Hello everybody, this lesson is going to cover some odds and ends for the thermochemistry chapter that did not fit nicely into earlier lessons. None of these topics are really large enough to warrant their very own lecture video, so I just threw them all together into one PowerPoint. Let's go over real quick the types of things that you'll see in this lesson. First, we're going to talk about a type of specific heat where instead of it being given to you in joules per gram Celsius, it's in moles. So instead of grams, you're going to have moles. Then we're going to look at how we can do these problems when you're given a chemical reaction. Next is learning how to label reaction diagrams. Then we're going to look at what are called phase diagrams, where you show people what phase is present when you have different pressures and different temperatures. Do you have solid, liquid, or gas present? Last, I'm going to show you a type of calorimetry problem where instead of putting, a hot piece of metal into a cold cup of water, you may have multiple phases present at the same time. You might have ice and water. And we're trying to learn how to do calorimetry problems where you have a mixture of phases present. We call that mixed phase calorimetry. So let's start with that molar heat capacity. So instead of it being the energy to raise 1 gram of a substance 1 degree, it's the energy it takes to raise a mole of substance by 1 degree. Instead of Q equals M cat, it's Q equals N cat. And as long as you make sure your units cancel, it's really no big deal. It's basically the same thing. So let's look at a quick example. A sample of barium chloride is increased in temperature by 3.8 degrees Celsius when the sample absorbs 2.4 times 10 to the 2 joules of heat energy. Calculate the number of moles of barium chloride if its molar heat capacity is 75.1 joules per Kelvin mole. So we're going to use that Q equals N cat problem. And the thing that's weird you might notice with these is sometimes instead of saying Celsius, they do like to throw in Kelvin more often. But do we care that it's in moles or that it's in kelvins? No, we don't care. We still just plug our numbers in, we still make sure things cancel, and we move on. Not a big deal. So let's kind of try to find these variables. Q, it tells me we absorbed 2.4 times 10 to the 2 joules. N is number of moles. We don't know what that is. That's what we're solving for. The heat capacity this time is a molar heat capacity right here. And it told me my delta T. It did the subtraction for me. We know that we changed by 3.8 degrees. Now, if you remember, a change of a degree Celsius is the same as a change of Kelvin. So that was that trick I taught you a while ago. You do not need to change this, just leave it. Plug everything in, Q equals N C delta T. If you'll notice, your kelvins will cancel. When you isolate your variable, your joules will cancel. And then you'll be left with moles. So if you gave 0.84 moles of barium chloride, 2.4 times 10 to the 2 joules of energy, the temperature will go up by 3.8 degrees. Okay, so you can see it's basically the things we've been doing. There's just a little twist. The odds and ends is that it's molar heat. We calculate it instead of in grams. All right, next let's look at heat of reactions. Sometimes you may see something like this. We give you a chemical reaction, and off to the side we say delta H of reaction equals, and then we give you some number. Delta H is the same as Q. Don't worry about it. Okay, we'll just use them interchangeably for this class. If your Q or your delta H is negative, remember it's exothermic, your energy is a product. Whereas if it's positive, it's endothermic, and your energy can be considered a reactant. You need the energy for the reaction to take place if it's endothermic. So if I were to combine 2 moles of aluminum, 1 mole of my iron oxide, I would get 2 moles of iron, 1 mole of aluminum oxide, and I would be seeing this amount of energy released when that happened. Heat of reaction is the energy for the reaction exactly as it's listed. So if I don't mix 2 moles, 1 mole to get 2 moles and 1 mole of this, I'm not going to get the same amount of energy. So we have to understand that this is based on the exact way the equation is written. So sometimes these turn into dimensional analysis problems. What if I want to know, how much energy is released if I only have 1 mole of aluminum? Then how much energy would be released? So what we can do is turn it into dimensional analysis. It's almost like the double dimensional analysis problems that we did way back at the very beginning of the year when we were trying to convert something like miles per hour. Well, this is the kilojoules per 1 reaction, the way it's written. So what we would do is we would say, okay, there's negative 851, so it should be 0.5 kilojoules per reaction. And 1 reaction worth has 2 moles of aluminum. So if we only had 1 mole of aluminum, this is the amount of energy that would be released. Maybe I give you a similar problem and I say, how much energy is released if you were to react 15 grams of aluminum? Well, you'd do 15 grams into moles, then you would see, okay, how many moles of aluminum per 1 reaction, how much energy per 1 reaction, and then you would find out how much would be released if you had reacted that many grams. So this is a way that we can kind of tie in our dimensional analysis and our mole ratios all into the thermo chapter. So give this one a try. Calculate the energy released when 135 grams of aluminum are reacted in this equation. So you're going to have 135 grams, and you're going to try to convert it until you get kilojoules. Start with your known value. We're going to go grams to moles using molar mass. Now, this part's a little different. We need to figure out a conversion factor that takes us from the aluminum into the reaction as an entire entity. So in this 1 reaction, the way it's written, there are 2 moles of aluminum. That will allow us to then use the heat of reaction to figure out how many kilojoules. You'll notice here that these are typically going to show up in kilojoules because it's a lot more energy involved than some of the other types of problems we do. So it's very, very common to see it in kilojoules. All right, switching gears again, another odds and ends is reaction diagrams. Oops, there we go. So for reaction diagrams, I've seen teachers kind of introduce this at all sorts of different chapters. I've seen people do it at the very beginning of the year. I've seen people wait and do it in a chapter called kinetics. I kind of like doing it here because we've learned about endo and exothermic, and that's one of the things you can see on a reaction diagram. So that's why I like showing it to you during this chapter. So a reaction diagram is going to be a graph, and it's going to represent the energy change as the reaction is occurring. So if we look, we have energy, and this is kind of like as time goes on, as the reaction proceeds. We don't usually put units down there, we just kind of leave it like that. So when the reaction is starting, all we have is reactants. Now, we usually have to get over what's called an activation energy peak. You need a little bit of energy to get the reaction started. That's because you got to speed those molecules up so that they collide really hard with each other so the reaction can happen. Sometimes you need to use some energy to turn the molecules certain ways so that they fit together like little puzzle pieces, right? Or that they collide in the right angles. So it takes a little bit of energy to get things started. Then by the time the reaction is over, you have your products. And so when you look at this graph, you can use this graph to kind of decide, is it endo or exothermic? Well, if I look, I'm going to end at a lower lower energy than I started, which means energy overall was released. And so that means this must have been an exothermic reaction. So if we want to draw an endothermic reaction diagram, it's going to look incredibly similar. We start with reactants, we have some kind of little activation energy peak, and we end with products. The big difference here is that in an endothermic reaction, we've absorbed energy by the time the process is finished. So the products should end higher than the reactants, like this. The difference between the reactants and the products is your delta H value, right? So that's how you find the change in energy that has occurred. You could find the energy it took to start the reaction, that activation energy. We'll do that more in another chapter, in that kinetics chapter. This difference is that heat of reaction that we just learned about, right? The difference here. Since people are always asking, even though we do learn about it more in the kinetics chapter, I'll give you a little brief overview of that activation energy. So delta H is the difference between the starting and ending places, right? Activation energy is the difference between where you start and the tallest part on the graph where you had to get to for the reaction to actually start to take place. So it's the smallest amount of energy required for molecules to be activated in order to undergo a specific chemical change. Really what that means is you need a little bit of energy to speed them up so that they hit hard enough. Molecules don't react unless they collide. And then you need the proper orientation for them to collide in the right placement. Molecules are three-dimensional, right? There's a top, a bottom, a left, a right. And if they don't collide in the right place, there may not be space and the right orientation for the reaction to actually occur. You learn a lot about that in college in a class called organic chemistry, where you learn about the direction that things need to collide. All right, on to the next odds and ends, phase diagrams. Phase diagrams don't get used very often, but I do think that they can be pretty helpful. So it's going to represent the phases at different temperatures and pressures. They look kind of crazy. They usually have some lines going all different directions. A lot of times they're different colors like this. They're kind of shaded in the various regions. So I think they can look a little overwhelming until you realize they're actually pretty simple. They're not telling you very much information. It's just there's a lot visually happening. So let's kind of break it down and look at the different sections. So what you're going to see is temperature on the X, pressure on the Y. You're going to see like three little sections, which makes sense because we have our solid, liquid, gas phases. You're going to see lines, which are where phase changes are occurring. You'll see some points that we'll talk about. And let's try to think about, why is this section solid? Why is this section the liquid? Why is this section the gas? Okay, so If I'm at very low temperatures, I'm going to have a solid, aren't I? Right? I'm going to have ice if I'm at a really low temperature. If I warm my temperature up, but I have a low pressure, that means I'm going to have a gas, aren't I? If it's warm but low pressure, then those molecules can be very far apart and I'll have a gas. But if I increase the pressure, pretty soon they get closer and closer together and it'll actually turn into a liquid, won't it? Let's say I have a liquid and I'm going to cool the temperature down. Pretty soon it freezes and turns into solid, doesn't it? So you can kind of think about ice as a way to try to figure out what section is what. Like, you know, if you are really cold, it's going to be solid. You know, if you warm that up, it will turn into liquid. If you lower the pressure, they can get farther apart, makes it a gas. All substances have different temperatures and pressures at which these things occur. The slopes and the directions and, of the lines, the sizes of the regions are all different based on the substance. Not a big deal. They're all going to have the same general sections. Let's look at those points that you can see, the triple point and critical point. The triple point is the point at which you can have solid, liquid, and gas coexisting at the same time under the same temperatures and pressure conditions. So if you get to that magical combo of temperature and pressure, you can have a container that has solid, liquid, and gas all together at the same time. Okay. Critical point's a little bit weirder. So you will notice that the line kind of stops. They don't keep drawing the line, do they? That's because past this point, the gas and the liquid end up with a really weird situation where their densities and kind of their properties start to mush together and they end up the same. And if their properties kind of become the same, then we can't really distinguish which parts are gas and which parts are liquid, which is a very bizarre concept, okay? So let me show you a cool picture I found that shows you kind of what's happening at this critical point. When we're at this critical point and we kind of move past it, we get what we call supercritical fluids. So down on the bottom, you can kind of ignore all the junk on here. Just look at the pictures here. So down in this bottom one, we have liquid and solid together, don't we? Here you can see that there's a difference in their densities. We can see that in this photo. There's a clear distinction between the phases. Well, once you get past that point, they kind of merge together, don't they? It's not really liquid anymore. It's not really a gas anymore. It's this weird thing called a supercritical fluid. They have bizarre properties. They're not really, one thing or the other. So we are not going to learn much about that at all. You don't learn much about that in college even, maybe grad school sometimes. It's a pretty weird, specific little thing in chemistry. But understanding that, there are pressure and temperature combinations where properties start to change is very important. Okay. All right, I'm asking you just a couple questions here. So a typical phase diagram for a substance is given below. At what point on the diagram do solid and liquid exist at equilibrium? So we want to know where on this graph are we going to have solid and liquids present at the same time. One of the things I always suggest is that you take 5 seconds and you actually label the regions before you attempt a problem like this. So I'm going to say, okay, at a cold temperature down here, this is going to be my solid. If I warm it up, it turns into a liquid. If I lower my pressure, they can spread out. This will be my gas. Now I'm going to answer the question. Just write an SLG, right? Just label it real fast. And I've noticed people have a much easier time with the questions when they can literally see the words on their paper. So I'm looking for the place at which a solid and a liquid can exist at equilibrium. That means that that's where the melting is occurring. Remember from our heating and cooling curves that melting, we have both phases simultaneously. So I'm looking for the boundary between solid and liquid right there. Point B is on that boundary. Anywhere on this line, you're going to have both phases. All right, let's try the next one. The phase diagram of a substance is given below. What occurs when the substance is heated from 100 degrees Celsius to 120 at 3 atmospheres of pressure? What I suggest on a question like this is that you draw lines to help you find your points. So we're at 3 atmospheres. So I just draw a line going across. Then I'm going to look for my starting and ending temps. Okay, I'm at 100 degrees. And I'm trying to get to 120. So now I can look and I can say, okay, on this line, I'm going from here into this region. I'm crossing from this place, this region, to here. This is solid, right? When I'm cold, it's going to be a solid. I heat it up, it turns into a liquid. I lower my pressure, it becomes a gas. So I'm going from the liquid region to the gas region. Well, when I go from liquid to gas, that is vaporizing. So that's kind of all we do with these phase diagrams at this point, is just making sure we understand that, at different pressures and temperatures, we have different phases, that the lines can show us where those phase changes are taking place, right? That's kind of about it. All right, next and last is going to be mixed phase calorimetry. These are calorimetry problems where you have a mixture of phases. And the reason that's an issue is that remember that if we're going to undergo a phase change, we can't just use MCAT. So for a normal calorimetry problem, we say MCAT equals negative MCAT. A little bit trickier here because we may not be having MCAT, right? We may have a combination of things happening. So when we have ice and water mixed together, right, we have a container of ice water. The ice is going to absorb energy while the water is releasing that energy. So we have two substances that are, transferring their energy back and forth. We're still calculating Q, but we are going to have to take into account the change to the phase of the ice. So, when the ice melts, the temperature doesn't change. But as soon as that ice melts, then we're switching gears, we're back to MCAT, and now we're going to have a temperature change. So we're still going to use Q equals negative Q. We're still going to be comparing the energy of, one substance to the other. It's just not going to nicely be MCAT and MCAT on each side. It's going to be a little more involved. So if we have ice at negative 10 and water at 50, you're going to have to heat the ice up. You're going to have to melt it, and then you're going to have to heat the water up a little. Meanwhile, the warmer water is going to be cooling down a little bit, isn't it? They're going to equilibrate somewhere in the middle. So we're still going to be doing Q is negative Q, but the ice portion, we have to do an MCAT to heat it up to 0. We have to do an ML to melt it, and then we have to do an MCAT to heat it up. The warmer water section, we just have to do an MCAT to cool it down. So instead of MCAT equals negative MCAT, it's one side is MCAT plus ML plus MCAT equals negative MCAT. So you can see how it's not new equations per se, but you're just layering on lots more pieces, right? You're having to do phase changes all at the same time as you're doing a calorimetry problem. Keeping track of things gets really awful. I suggest that you try to be careful with how you label things. Some people like to color code, right? That can be very helpful. Whatever you do, you're going to have to work hard to keep track of which numbers go with which portions of the equations go with which, set of water. That part can be tricky. Let's do one of the practice problems from worksheet 7. Number 16 is a mixed phase calorimetry problem. And rather than doing a whole brand new problem for our notes, let's just do the one from our homework. I'll give you a little head start on your homework sheet. So, determine the final temperature when 18 grams of ice at -10 mixes with 275 grams of water at 60. Now, conceptually, you should be able to notice that this will probably end up closer to the warm water, won't it? If you have 275 grams of warm water and you only have 18 grams of ice, you're going to end up pretty close over here. We will give you problems where it's pretty obvious where things will end up. So, let's do our little cartoon. We are starting at -10. We are also starting at 60. That's where this gets weird. Okay, we have one set of water that's going to be warming up. We have one set that's cooling down, and they'll meet somewhere here in the liquid area. So the cold water is going to heat up. The hot water is going to cool down. We're going to have to heat that ice up. We're going to melt it. We're going to heat it up. Meanwhile, this stuff is going to cool down. And we will equilibrate somewhere on that line. And think about it, if you put some ice into a cup of water, it'll end up water at the end. It'll all end up liquid. It will all melt. It'll be a little bit cooler than you started. That point there is the final temperature of your mixture. That's what we're looking for. So, if the cold water heats up, Q, and the hot water is cooling down, negative Q, we're going to end up with a Q equals negative Q calorimetry problem. We're mixing two waters together. We just have to phase change it somewhere in the middle, right? Just a few more pieces happening over here. So like we did before, let's list the segments that we'll use. For the cold section, we'll heat up the ice with line 1. We will melt the ice with line 2. We will heat the water up a little bit. Then, for the other liquid, right, the other water, the warmer one, it's going to cool down by using segment 3. We'll be going the other direction. It'll be coming down this way. Now we're going to basically figure out which equations to use, and we're going to plug them into the Q equals negative Q calorimetry concept. So we're going to have Q1, Q2, Q3. We're going to do an MCAT. We're going to do an ML. And we're going to do another MCAT. But look what happens. We don't actually end up with a delta T here, really, do we? We don't know what delta T is. We know that this is going to start at 0 because it's line segment 3. But we don't know where the water is going to end up when it's finished. So you're going to leave it as TF. Okay? distribute all this out, and you get 75.24 times the final temperature times TF. Just leave it like that, okay? What's your total Q value? Just like before, Q1 plus Q2 plus Q3. Add them up. The only thing that's going to be weird is these two numbers will add, and then you got to kind of have this stuck on the end over here. Now let's find our warm water. Q3 is going to be an MCAT. We have our mass. This time, look, the masses are not the same, are they? This was the warmer water. We had a lot more of it. We have our specific heat. Our final temperature, once again, we don't know our final temperature. We know that the warmer water started at 60. So that's what I get. Just like before, distribute it out. This one will be a little more complicated, right? Because you have to distribute to the TF and you have to distribute to the minus 60. Just be a little careful. Now that we kind of have all our pieces, let's kind of think of the calorimetry part. We know that we're going to have Q equals negative Q, equal and opposite. Energy absorbed is the energy released. You're going to take the answers over here because you know what Q cold and Q warm are. And you're going to plug those in. But here's a quick suggestion. Because of this negative sign, you have to distribute that. We get double negatives. People make mistakes. Here's my suggestion. Just move it to the other side. If you have Q cold equals negative Q warm, and you do plus Q warm, one on each side, you're going to end up with this, aren't you? I don't know if you remember from algebra, but when you were trying to solve quadratic equations, do you remember how you tried to get it so that 0 was on one side? That's the same thing we're doing. Right, we're exploiting a fact of algebra that can make it easier so that we don't have as many algebra mistakes. Just move everything to the other side. Now do Q cold plus Q warm. And now you're going to combine like terms. You're going to move things around to isolate your variable. Divide both sides so that you get TF all by itself. And you're going to find out when you put those two things together, it's going to end at 51.1 degrees Celsius. You put ice into water. The ice heated up. The ice melted. The liquid warmed up a little bit. The warm water cooled down a little bit. They equilibrated somewhere in the middle. By the time you're all done with all those numbers, you find out that you ended at about 51 degrees. Please, always at this point, stop and check that your final temperature is somewhere in between your starting temperatures. If you end up with a temperature colder than you started, right, if below -10, or you ended up with 105 or something, right, that wouldn't make any conceptual sense. It would alert you to the fact that there was probably an algebra mistake. So always stop at this point and make sure that it makes sense with the concept of that you should end somewhere in between your two starting substances. Okay. All right, everybody. I know that was a lot of random things thrown into one lecture, but I hope you can see that it was not, worthy of 5 separate lecture videos. They were all kind of little bits and pieces. So you will get to practice all these kind of random things on worksheet 7. And then, as always, ask questions if you need help. We have extra starred worksheets if you need extra practice. All right. That's it, everybody. Hope that was helpful. Bye.